Hey guys, how's it going? Welcome to another episode of Ferris Makes Emulators. This is episode 33. Wow, that number's getting big. Bug squashing part 9 even. And that number is getting more concerningly big. So the past few weeks, still been working on this graphics memory corruption bug. And I did a bit of thinking. So last week, we basically ended with me dumping some save states. I wrote some code to automatically detect when our sort of clobber state, as I'm calling it, occurred. And then when that happens, we can sort of save out some save states and also write out some HTML that shows us some diffs between some of the save states. So particularly, we enter this graphics decompression routine, and then an interrupt happens. And when those two conditions happen, we grab the state of the emulator as we enter the interrupt and as we exit the interrupt. Or maybe it was as we... Hold on. Maybe it was as we enter and exit the decompression routine, but I don't think it was. I think it was entering and exiting the interrupt. I think. Hold on. Yeah, it was as we enter and exit the interrupt. Now, I was thinking about that because, yeah, and then if we clobbered, I also changed the file names so that we can actually see that. So, for example, some output of that looks like this. We get the different HTML files that show us the difference between the save states, and those look something... Whoop, don't want to pull the whole tab over. Looks something like this. So this is the entire 64K of memory from the system, and these red locations are showing us where stuff changed. I also should probably mark stuff that's not 0 now that I'm looking at it, just to make that a little easier to read. But yeah, so fairly straightforward. Now, I was sitting here thinking about this before the stream, and because still the challenge here and the reason why I'm doing all this is to try and figure out what parts of the system that are changing here are actually relevant and which parts aren't, so that we can actually spend time focusing on the parts that are relevant and ignore everything else. Because still, the big problem here is that there's a bug. We don't know exactly what's causing it. We need to figure out places to focus and spend our time. Now, as I was thinking about this, I was thinking, okay, so the difference between the start state and end state when the clobbering happens and when it doesn't may not be that useful, because I started looking at some of these dumps. Basically, all the dumps that I have where the memory or where the register clobbering doesn't happen, none of the RAM actually changes during this interrupt, which is somewhat interesting. And what that made me think was that instead of comparing the memory before and after the interrupt happens, I should actually try and compare the memory before the interrupt happens when we don't get a clobber, and the memory before the interrupt happens when we do get the clobber, to see what state has changed so that when it enters the interrupt, then a clobber occurs, if that makes sense. So now I suspect that there's going to be some other stuff in RAM changing between those, so that's still going to give us more information than we need. However, I think then by comparing a couple of those, some of the outputs from those, we can see sort of what is normally changing and then what has sort of changed specifically between these. So I'm thinking there may be something interesting there. But yeah, going to keep digging, or start the stream by just continuing to dig like that, more or less. By the way, hey, Dark Second, the only one who said hi in the chat so far today. Actually, I should probably tweet about this, because this is lower viewers than I normally have by now. 1 second. Oh, Vid, how's it going? So I think I think the first thing I want to do is I want to actually mark all the bytes that aren't 0, just to make that a little bit easier to see. Another thing that I wanted to do is I had some dumps here that I took from the debugger. And these were all 16 bytes wide. Now, in these dumps, I made it, I think, 64 bytes wide, just because that was kind of easier to get like a high-level overview. But I'm seeing only very small bits that have changed, and I think comparing it to this would make it a little easier if I went ahead and, yeah, it actually made it sort of match this format. So what I'm going to do is I'm going to print the full address here when we're dumping, and a couple other things, just to make these dumps as useful as possible. So we'll do some of that. By the way, guys, check out what I finally got from Wobble. Nice coffee mug from Revision. It's got I1 Revision on it, which I'm tempted to write almost in marker. And then the Revision logo on the other side. Naturally, I'm being careful handling it because it's full of water, but yeah. Had to share that. Yeah, so let's first check out this output. I'm going to delete the dumps that we have here because these are so easy to get now. That was something else. I think I still have a bunch of these heat map colors here, so if I just repurpose one, that should help. So first of all, yeah, here we go. If it's 0, we do this heat map. Or, oh no, that's actually ending the thing. So actually what we want to do here, this guy is going to be our address. So I'm actually going to make this 8. I'm going to add OX here. And we're going to do 0x0500 0 or I. And then I'll plop this address on the end of this. That should be good enough for here. And then what? Yeah, here, if they were different, we're going to have this. And we always write the byte. I'm just going to do this. So it actually doesn't matter which one of these we use because we know that they're going to be the same here. So we can just say begin byte is not 0. We don't need a title here. And we can use, I don't know, heat map 3 or something. Let's try that. There we got some states. Here we're going to get some clobbery states. Nice. So now when I look at one of these, we get, yeah, this looks a bit better. This gets a bit easier to see a bunch of these that were not 0. So I think that's pretty cool. Really doesn't use that much of the memory, which I find is actually pretty common in games and demos alike. Although I think I'm going to use a different heat map color for the non-0 values because I kind of wanted it to be green. maybe heat map 4. Should be enough. Yeah, nice. And then the other thing I was going to do was change this column width, which I think I did here. So that's nice and easy. Yes, there's anime in my browser. I don't know if you guys are catching that when I'm switching tabs. Watching a show called To Be Hero, which is ridiculously weird and funny. If you like One Punch Man, you might like this. And if you don't like One Punch Man, I don't have much further to say. Yeah, so now, of course, this stuff is a lot taller. But it doesn't really make it that much harder to look at. And the reason I also want to do this was because, like, comparing to my notes. So, for example, we can look at, like, where was one of those values? Like, let's say I look at my notes here, and we have 2290 starts with FF. So if we go to 2290, okay, we didn't see FF there. Which may actually be interesting. May not be, but you know. Darkskin says, add some spacing between the words. Yeah, I might do that. How's that GBME going, by the way? Let's do... Easiest way is to do this, actually. Or I'll actually write out a space here. No, we'll do here. Yeah, that period after you've done a lot of the CPU, and then you kind of have to blindly start implementing the other hardware is a bit daunting, but until you run into bugs like this, it usually gets easier. By the way, I do have my audio turned off. As I'm listening to music. Hey, Daniel Colin. Yeah, this looks a bit better with the spaces here. That's nice. Cool. Now, the easiest way to start comparing this stuff, I think, to run this again. Actually, those dumps were still good, but you know. I'm going to run this when it clobbers and when it doesn't. And I just want to look at a couple of these. So for example, if I look at like any of these ones here in the beginning, we should get none of these have any changes, which is already somewhat interesting. You know what I just actually realized is a really obvious thing I could do here as well? I should actually look at which memory addresses are read here. I don't know why I didn't think of that. I'm going to do that. We can mark those in a different color as well. In fact, if I turn these back to that light blue for the ones that aren't 0, and then use green for the ones that are red, that might look pretty nice. Yeah, how might I do that actually? Let's figure that out. Because that will tell us, like, when it doesn't clobber, which memory addresses did it read, and then decide not to clobber. And then we can look at the differences between those dumps. I think that might actually be really nice. So let's do that. Hey, Michael C. So I think, because I definitely do some stuff for watching. Yeah, here I do. Oh, that's for the reg GPR. But I definitely do this for the memory instructions as well, which I'm pretty sure is only a few of these. Yeah, like here. Ooh, Daniel Collin got a frame meister. I would be super jealous, but I'm only a little jealous. These are really, really good for like upscaling and capturing. But I've got a pretty decent capture unit myself. This is some StarTech thing. No pass-through on this, unfortunately, though. But instead, I have a composite video splitter, which works out pretty well. So yeah, congrats. But I'm still more jealous about your broadcast monitor. And I'm hoping my MSX arrives before Solskogen, because then I'll totally take that with. Oh, cool. I didn't know you were looking into doing some streaming stuff. Sounds cool. I went with this one as well because it was small. I can't remember the name of it. Oh, here it is. USB 3 HD cap. It's the same chip as some other thing. So I had to do some weird hacking and stuff for the drivers, but it works out pretty nice. And because it's so portable, I want to use this for like part of my mobile old school development setup. Ended up being a pretty good choice so far. Although, of course, there's definitely some lag if this is all I'm using, but it's pretty nice. Hey, Zamak. Okay, so I want to... Right, half word. Really, I want to get all the reads and writes that occur here. I think what I'm going to do... Because I think we have read bytes, read half word, and I think that's the only way we can touch the bus. I think we can only do... Oh no, because we do also do read words here, but I think that is just 2 half words. I'm thinking that on the interconnect, I can just add a little dictionary for all the reads and writes that happen. And then, yeah, sort of enable and disable storing those. And I think it should work out pretty nicely. So if we do, for example, this, we'll do pub I can see you started working on a PSX emulator in Rust. Awesome. I have to tell one of my colleagues that at work because he's going to get jealous and start working on his more, I hope. That's really cool. I hope he found, I think it's Simios is how you say that. I hope he found his resources because he started publishing some pretty good stuff on that. I think we'll do this. Do an access thing here. And then we can do byte access. Or we'll do this. We'll do a byte read. And then we can get the adder here. We can do a byte write. U32, U8. Oh, I love ADTs. We can do half-word read. U32. Actually, I'm not really concerned too much with what was written. But why not? I'll just not use that in the output. Yeah. And actually, we don't have word reads at this level, and I don't think it'll make much of a difference which kind we log. I think this will be sort of the best we can do. So we'll do record accesses, and then we'll do a... We'll do a set. We'll do a hash set of this, I think. Because we only care about sort of unique ones here. I think that'll be good. By the way, I'm very happy to hear about these emulator projects. So keep sharing. Yeah, I think this is really all we need here. Except of course we need to where access is false here, and accesses is hash set new. And then we'll do this stuff. So I'm gonna actually take the non-masked address here. So do if self.record accesses, self.accesses.insert access byte read, and then we'll do the address. Oh, how nice is that? That is nice looking code there. Do this. So Mark is still working on his for the Game Boy in C#. Nice. Ah, yeah. Test ROMs and screen hashes. That's a good idea. Especially for those test ROMs that actually output to the screen. I probably would have actually just saved the pixel data. But the hashes are going to be a lot smaller and quite fast to compute, I'm sure. Or I should rather say I've previously done that using just the actual pixel output. But to be fair, that was actually... yeah, that was actually testing the visuals. And the nice part about that, actually, you may want to consider that, because then you can actually look at the output. Well, I guess you can anyway, but it doesn't match. I don't know. Nice idea, though. So now we should basically just be able to toggle this, and then we'll get the accesses. So what I want to do is here, I think. Yeah, 'cause it's going to dump the state here. So I want to do this. Yeah, when we enter and when we exit the interrupt. Perfect. Now I think, yeah, we'll definitely get some of these accesses that are just going to be stack manipulation. So we're going to want to ignore those, but we'll probably have to do that ourselves. But I think we can do, don't think this will be too bad. I will do self.interconnect dot record accesses. It's true, and we'll do clear the accesses as well. And we're done. We're gonna set this to false. So we don't do this all the time, only when we actually have to. Otherwise, we'll totally explode memory and some other things, I'm sure. I think we're good there. And then in the output, I want to do this. I think what I want to do Okay, I think, what am I thinking? So we have self here. Yeah, I can actually literally just do this. I think we basically want to search the accesses and find one that accessed this address. So I think we just do self.interconnect.accesses.iter.find. Dot map anything we find to true.unwrap or false. And then here we've got the access. We can match the access. And we're either going to have an access byte read adder or access byte write, or we just want the adder. And here it's going to be if the is equal to or I, like that. In fact, I think we can do this. Let's stick the adder here. Oh yeah, except this, so we'll do, let's call this byte adder. And then in this case, we want to do if the address is the byte adder or the address plus 1 is the byte adder. And that covers all our cases. So I think that's the logic there. I'm just going to compile this really quick to see if that was correct. Okay, so we're going to do this as U32. And that should help. Oh yeah, we need EQ and hash on the access type, which means we'll also need partial EQ. That should work. In fact, I think actually we don't need hash here, but we might. Okay, we do need hash there. And then expected a reference, but got the type here. Okay, let's just do this then. No worries, Amok. I can just repeat it. What I was saying is that you might want to consider actually outputting the images and comparing those, if for nothing else, just to make sure that you can always look at them. But maybe that's not helpful in your case. Especially if you output them in like compressed PNG or something. Then they tend to be very small. Oh, okay. Hold up. I think if we do something like this, then it probably works. Yeah, perfect. Then you're good. So this now should be doing checks if these were accessed. But then we need to also use this. We'll put this in here. And we'll use 4 here, which will be yellow. Stick that logic there. Yeah, so if it changed, it's going to be red. If it was accessed, it'll be yellow, and then if it was not 0, it'll be a lighter blue. Otherwise, it'll be blue. I may want to swap these ones, but I think I want this. See if they changed. Okay, so for example, now we get these ones that were accessed, which is actually really cool. Touches a lot more memory than I would have expected, actually. In fact, here we got some more changes that I didn't expect. Somewhat interesting, because I didn't see those before. Interesting indeed. All right, let's get some more data. Yeah, that doesn't sound bad at all. Zalmauk. Really nice try to say that. So this is one where we did get a clobber. I'm actually going to add the title of the file here, because I can't read it here. I'm just going to do that in the output here. It'll be a little thing, but it'll make this easier for me to look through, which is what matters. Here is our file name. think I want to do this here. And then, yeah, here's the title here. Should just be able to do that. So now if I pull one of these up, I get the title here, which includes the extension, but that was fine. So here again, we have not that many that were touched. And in this case, none that were modified. Which is pretty cool. And then we have one where things were clobbered. You can see it touched the same addresses here. In fact, the same values as well, which is pretty interesting. So like basically what I'm looking for here, this is one where the clobber didn't happen. This is one where it did happen. Basically, if like maybe some of the memory here, like I'm looking at these values that changed or that were accessed, and because they're the same, I think we can rule out those addresses. Just gonna look for the first thing I see here. 502020. Somewhere around here. You can see here some of the values were different, which may be significant, but they weren't red, so they probably don't have anything to do with this. So that's interesting. And then a little bit lower down here, you can see here we start reading a few different values. In fact, this only reads this, and this looks like it reads a few more. It also starts writing some stuff. We also always get these accesses here. Be interesting to see if the one that clobbered this following that one, how different that was. And then we have a lot of changes beneath here. Which could mean several things. Do we have much else going on in here? Probably not. Down here, actually, we have some stuff. I think this is where our stack was, but I'm not sure. In fact, I'm a little bit surprised, actually. Oh, you know what? Actually, I just realized something. So in this first one, where this first decompression routine happened, I think we had some writes here, around this region. And then the subsequent ones we don't. And actually, if this is our stack, that totally makes sense. Right? So what I'm thinking is that so this 0, 1, 2, and 3, those all happen at the very beginning of the game where it's loading the initial graphics for the title screen, I believe. Interestingly enough, I think no sound is playing for that. So basically, I'm under the impression from the last weeks that it's the sound routine that's clobbering the data. And something is supposed to have like disabled the sound before before the frame interrupt happens. Probably. Anyway, if these values are our stack, so as you can see, when I go between these, a couple things down here change, but these values up here don't change, and that would be sort of the most recent values if our stack is growing downwards. So what I think is happening here is that we get these writes here that are different because this was the first time that we entered and exited this routine. And so it's going to write these return addresses on the stack here. And then on the next ones where it happens, it's going to, of course, access those memory locations in order to like read and write the values for the stack. But they're not going to have changed. So that's probably what we're looking at down here. So I don't know how to disable the sound. I can disable the sound hardware, but it's not disabling any of the driver code that drives the sound. If I can figure out where that is, then I can do that. Which maybe I can find that with watches, but that's just my gut feeling after the stuff we've seen now. Oh no, I can definitely disable the bugs when I disable the interrupts. That we've been over. But it's not the whole story. Like initially I thought that, oh, it's the interrupts that's causing the problems, and I don't think that anymore. I think that the interrupts are supposed to happen. Just gonna scroll here so we get the alignment. I think the interrupt is actually supposed to happen, but then there's some logic that executes some parts of the interrupt that aren't supposed to occur. That's what I think is happening. And then, so these other values here that are different between these two captures on the stack would have been like other functions that were called between this stuff happening, and I don't think that's probably going to be relevant because none of the clobbering happened. What would be most relevant is these values that are here, and those seem to be the same things. But I think that's why we're getting writes only on this first one and then not on the other ones, because that seems to be consistent between runs. And then this one, of course, a lot of stuff has changed. And in fact, you can see more data down here further down in memory, which if that's the way our stack is growing, then we would have, done some changes down there. If we would have gone into some other routines, it would have changed things, which could make some sense. But I think I can run this in the debugger and check where our stack pointer is roughly. I can't remember which register was the stack pointer, actually. I know it was R3, wasn't it? So let me... where did I put this? Or also, actually, if I disable the interrupts, the game stops working. So it needs those to run. But if I didn't trigger the interrupt, it's on certain conditions, then of course the bug goes away, but that breaks other games. So that's why I try to hammer on that. I really wish it were that simple. Here, what I want to do is I want to just stop on any of these, actually. So we'll do F12 here. Add a breakpoint. Whoops. Continue, so that'll break when we get our decompression routine. And I just want to look at... actually, I didn't have to break during this, but I just want to look at our R3 3FB0, which is right here, this guy. So that's definitely our stack pointer, and this stuff here is definitely our stack. So again, I think that's why we're getting the writes here, and otherwise we're basically getting accesses. So that's actually what I should do, is I should recapture these and change the color slightly. So I should do one color for reads and one color for writes, where writes would take precedence. I think I want to do that. And then I'll use a different color for, or I think that's actually all the colors we need. So I'm gonna do that and sort of recapture these. Debozan, can you add a history of interrupts fired and to be acknowledged in your heat map? That may help. I don't think so, because we know it's this one kind of interrupt. It's definitely this one kind of interrupt, and it definitely happens in this certain condition. And I'm so certain that it's logic inside the interrupt, not the interrupt itself. That's the problem here. So I think I won't need to include that. So we'll do was read and was written here, just to separate these out. So we only care about writes here. And then anything else will be false. We'll do the same thing here. And then here we only want reads. Yeah, let's do that. And so then we'll have we'll copy this, so we'll get was read. So then we'll do written is 4 and read is 5. And I'm actually gonna separate these. Let's do, instead of 3, 4, 5, we'll do 2, 3, and 4. The reason I'm doing that is to just make sure we don't go too far into like the red, orange, so it doesn't look like these are values that changed. Try that. Okay. This may have been too close now. I might want to shift those again, actually. Looking at this. So here we're getting stuff that changed. And then you'll see blue and then another. I think this is the red color, and that's going to be too similar to the other one. So I'm going to put that back. Okay, so now we have our normal values, our values that are not 0, and I'm pretty sure this is reads, this is writes, and then we'll have the differences as well. Although, I actually think I mixed up the colors I wanted to use for the reads and writes. Yeah, I did. I want to use the darker one for writes and the lighter ones for reads. And then I think this looks more like what I expect. So basically the green should be ones that we read. The yellow are the ones that we wrote. But they aren't different between these. Right, and then we'll definitely get the writes here on the stack, which is what I would have expected. So that's nice. And then red are ones that changed. So for example, whenever this interrupt occurs while the decompression routine is running, all these values are red, but they're not written. And if we compare, for example, ones where there was and was not a clobber, the values here don't change, so I don't think they're significant. And then the ones here weren't touched, so we don't have to worry about those. So again, don't have to worry about this beginning part. Gonna ignore all that. Let's go down to here. This range here we don't have to worry about. Wasn't touched. Here we get our major differences. Now we always write this actually. So interesting. Read some of these. Very interesting. We always seem to read all these. I'm not sure what these are. Also, if I look at, I'm gonna get new dumps. Make sure I get multiple ones where stuff is clobbered. Because I have a feeling by comparing multiple of these, we'll sort of get at the meat of what's happening here. Definitely not the fastest dumps in the world, but that is not a problem. Let's open all these. Oh, that opened a lot of tabs in a specific window that I didn't want a lot of tabs in. And in no discernible order as well. Fun. Okay. That didn't help either. Should be enough to look at. Yes, again, this stuff at the top, nothing is different for any of these. Except it does read those values, but they're not significant. Which is good. Also don't expect these to be like any different here. So already like some stuff here is interesting. Like the fact that it at least writes all these values and reads these ones, but nothing changes between these. So here already stuff has changed here. So interestingly enough, I think it was these bytes we were looking at here. Like I'm just seeing O and OC, and that sounds a lot like what we saw here. 2280, and here we have 2280 is here actually. But yeah, this is actually 8 bytes away from that. So that's actually these values here. And there we're already seeing there's some difference here. 0207, 020C, and we get a clobber, 020C here, or 10C, 020C here. I'm lining these all up. 20C again. 20C here. We get some differences in here, which is somewhat interesting. Mostly reading. but also writing. Maybe that's some sound playback stuff, which would explain why nothing changes here. Although we definitely get some other values here, which is somewhat interesting. A lot of stuff down here, which could be also, like if this is sound effects, that could be relevant. Seems like a lot of memory to keep, though, for just playing sounds, but could be what that is. Just load up these other ones as well, just to look at as many as possible. I cannot tell you guys how happy I'm going to be when we figure this out. But I really, really want to do it. Did I mess up the scroll here? Looks like I did somehow. There we go. So it is interesting that, like, when we do get more of these changes, they're all still within, like, these blocks of memory, whatever those mean. In fact, I wonder, actually, because I'm looking at these values here, like, one of the things that always happens is it always reads, regardless of whether or not it clobbered, it always reads a bunch of these. I wonder what those are. In fact, I seem to recall there being a loop where it, like, goes over a bunch of these. If, for example, this was sound playback, it might actually be that these are for the different voices. But then again, there's more of those than I would have expected. So maybe it's something else. So, like, for example, here there's a bunch of zeros. And then here there's a bunch of, like, in the ones that change, this value here is always something other than 0. Which may be somewhat interesting. And it only reads them, which is also interesting. So there's only 5 sound voices, which is why it's kind of weird that there's so many. If that's what that is. We get a lot of activity down here. In fact, this goes quite a bit farther than just those few, so I'm not really sure if that's what that is, actually. So the reason I'm thinking it might be sound is that in a 1 or 2 weeks ago, maybe 3 weeks ago, we were printing out audio registers and just noticing that some of those were changing whenever we got corruption. That's kind of why I'm thinking that. May or may not be relevant. I don't think they're compressed samples. As far as I remember, when I studied the compression routine, it didn't touch any of the audio memory. It only Like it had sources and destinations. I think all the destinations were within video memory, if I remember correctly. And even then, the samples wouldn't be that long. Because they're only, I think it's 32 bytes and they're 4-bit or something, so it's not very long. I think there's a little more data than that here. So maybe it is that, maybe it's not. Not entirely sure. Now, one of the things I might actually want to do here. 207. One of the things I kind of want to do here is I noticed that this value here, I think that was the one we were looking at. I want to just see what happens if I write a 7 in there whenever we get an interrupt. Just to see. So this is 228, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 2289. Just to try something here. And I'm going to disable the state dumping here. I'll do interconnect.write byte. What's this again? 2289. The other thing that's interesting, it seems to always read this as a word, which is what I think we saw in the code. Interesting that it reads and writes it every time, but yeah. So let's just see. In fact, I'm actually going to enable my system audio here. In case there's... Sorry, I said in case there's anything interesting. 1 second. I want to see if it affects the sound and if it affects our clobbering. Okay, so that didn't fix it. So at least we know it's not just that. Right? Because what I did there was when we entered the interrupt, then I changed that value. So we know at least it's not that value alone. And in this case, 010C. Let's actually store this whole value here, or at least these values, 0207. So if I do 88 and I do write half word, and we get, this is going to be little endian. It's going to be 0702. Let's just see what this does. This is one of the cool parts about emulation is you can just do stuff like this. So that changed the corruption, or it changed the graphics at least. I'm not at all convinced what we're getting here makes any sense, but it is something that affected something. I actually want to just try writing out this O2 here. Although if I remember correctly, it seemed like that was the screen it was going to or from or something. It's interesting that the sound just totally stops. And of course, we still get a lot of corruption. That's when I write that first byte. So I think it's probably not this, even though that seems to affect the compression or the clubbering. I was originally kind of suspecting that value, and now I'm suspecting it less. Hey, local hoster. Yeah, let's try, let's take DarkSecond's suggestion here and try setting a bunch of all these. They seem to be 64 bytes apart, starting at 22cc. And we have how many of them here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is that correct? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, we have 12 of those at 22cc. Let's try that. We'll put this back, actually. Who knows what this will give us? But let's see. Suddenly our sound got slower. Not at all the result I expected. Very strange. Now, was that related to sound playback? It did change the rate of our sound playback, but I'm not convinced yet that that was the thing here. Not convinced yet that that was related. Let's look at some other values here. Because, like, that could have been stuff for sound playback, but the fact that it affected the rate makes me think it was something else. Yeah, there's also the one at 22BC. Or, yeah, it gets changed here. In fact, it's like always 2C in this case. Let's see if I grab this value and I always write this 3737C8C8, or yeah, that'll be what it is in that Indian, and that'll be 22BA. That affected nothing. But considering it gets written here, that might make sense. in the spirit of just trying stuff, let's try setting 2290 to 0 every time. Because it would be really interesting if we could find some combination that fixes the values here. Or that fixes the corruption. Even if it breaks something else. Okay, so that broke audio. At least this first track playing. But it didn't break the corruption. And that's interesting. So that was changing this. Now, what other things change here? I see these values that change. So let's just try affecting some of these, see what happens. This is A1 here. Let's try making that. It's BC here. Let's just try making it A1 here. A0, 1, 2, 3, 4, 5, 6. 2 to A6. And that was A1 that we wanted to set it to. I mean, eventually, we've got to hit the thing that matches here. It may be multiple things as well. Okay, it wasn't that one. What other values here are red that may have changed? So like, Jeff, was there values read in the interrupt handler that made the interrupt code jump all the register clobbering? I think it made jump over all the register clobbering, and there were, but I had a hard time telling what they might be. I just thought that this might help me get a better overview. So this was the A1 that I just tried. I think I'm going to try some of these here. Although they're at least written here. I don't know if they're red or not. Yeah, let's just try this. No visible change there. And that might make sense, because if these are just being written, then, you know. Let's see. Hold up. Just gonna try this one. These two, rather. Although, again, these are written, so it may not be relevant, but we'll see. I'm going to grab some more states here. Actually, I need to not be doing this, or I will contaminate my data. Or contaminate my samples, I guess the right term there. That's not what I wanted. Warp mode. In the spirit of SGDQ happening next week. Warp mode hype. I don't think there were any cases where it didn't clobber after it clobbered. I don't think I've seen that at all. Not sure if this is the same one that I had before, but we'll see. Yeah, these are the same. Oh, that's kind of annoying. Come on. Yes, so I didn't get any of those written. That can't be. Then I should have gotten exceptions at least when it tried to overwrite the files. Dang it. Yeah, Fuzz, I use Emacs on Mac. I believe this is in my FAQ. Oh, yeah. Yeah, you're right. I did disable dumping. It wasn't for speed. It was while I was doing these writes. It was to not contaminate those. Oops. See what happens if I do a lot of these. Probably weird stuff. Probably weird stuff. The really interesting thing here is that it's not affecting the compression. Which writes? So I know I just say, or I removed a couple of these that I tested out with. I'm gonna order these. Yep, it's these ones. 2288. Probably remove those. Or 207. Wonder if I can get a combination. Actually, I'm going to do this as bytes. Wonder if it's at all possible for me to get some kind of combination here. That might work. So the only thing I can seem to get it to affect is that the graphics look slightly different. Definitely disables the sound, but we're still getting clobbering, and that's what's kind of concerning me here. I wonder what one of these dumps might look like after I'm doing this stuff. Let me start dumping these again. Yeah, and Fuzz, yeah, there are other emulators that are open source for Virtual Boy. I have not tried Spacemax. I'm not particularly interested, to be honest. What was I testing here? I totally forgot. Oh no, yeah, I was just dumping the states while doing this. So I'm guessing the number 4, for example, that we wrote out here, should be different than the other one that we have. And what's hopefully interesting about this is that we would see some differences here. So this is where I didn't overwrite the values, and this is where I did. So for example, you can see like the 0207 here. A bunch of the writes that we got get overwritten, which is interesting. And then, yeah, all these values were 0. Now, some of them still change down here. Zero Pent, I thought you had this stuff without corruption everywhere now. And then before would be nice to compare the memory layout in the same scene. Not really sure what you mean. Yeah, I'm getting a little distracted. I'm going to kind of ignore the chat for a little bit if you guys don't mind. Sorry about that. Just going to close that for a bit. Let's see if there's anything else down here that's particularly interesting. Again, these shouldn't really be any different. I should actually look at one of these here as well, from when I'm overwriting these values as well. Even though this shouldn't change at all, because I'm basically writing the same value. So we have a couple memory locations that have changed values, but basically nothing else, because I'm basically writing in the values from this other dump here. So it should be the same. Yeah, some things in here that are changing. Nothing appears to be significant. And that is probably leftover values from like stuff that ran at a different time. So I think that's not going to be significant. Also because they're not read or written. Shouldn't really matter. But it's kind of cool to see them actually be different. Here again, even though we overwrote these are still written somewhere, which is somewhat interesting. I think, actually, what are some of the notes I took before? Because if I have some notes about some of these values, for example, 2288, definitely have more notes than that. Yeah, these I don't think affected the clobbering at all. Yeah, because in the dumps we can see that those are basically not read or written. Okay, here's 2288, which didn't seem to save us from the clobber. So interesting that now that we're changing those, it also seems to be the case. 22cc here. So interestingly, here's probably the loop that is doing those 64 different writes that we're seeing here. Or the 64-byte apart writes, I should say. Let me scroll up again because I don't know if this is going to be that relevant down here. A little bit clumsy the way I've set this up, but not the worst in the world. Especially for ad hoc output, this is pretty good, I think. So I think yeah, sorry guys, I'm just getting way too distracted. Need to just sit here and think on my own a bit. Of course, that was after I wrote those values. Okay, so here we also see compare 12, which is interesting because I think there were 12 of these that I decided to overwrite. So that's probably what those are. You know, I wonder. I think it was. Where was it? Here. Yes, this exits the loop. And we're basically going to be done. This A4, I think, is what we jump. No, it's not where we jump over here. B4, maybe? Yeah, so that will basically skip everything. I'm wondering. I honestly wonder what'll happen if I just change the ROM. Wonder if that would be useful if I just changed to like always skip over this. So I wonder if just to see where some of these might happen. But I think the thing that bugs me about that is that changing this value here should have the same effect in this case. So it ands it with 8 here, and then if it's 0, so it ends it with 8, and if it's not 0, so we're going to check that one bit here. Then we're going to jump to B4 down here. And we're definitely not going to have clobbers then. So if I do the 2288 value, so here we had, that's this one. So instead of writing like 0207, I'm just actually going to write to 2288. I'm going to write 8. Let me disable dumping for now. And I think if we do that, let's just see what happens there. right? That I expect to at least stop the clobbering, but it might stop other stuff. Okay. So that at least definitely saves us from clobbers, but of course it breaks other stuff. But I expected that. That's something I expected to happen because, yeah. Once again, I want to see it go into demo mode and not a clobber. But we expected this because the logic there is really simple. It basically skips over everything. Yeah, no clobbering there. I want to see that happen again, just to be sure. Although, yeah. So I also think that this proves that most likely it's not the fact that the interrupt's firing that's causing the problem. Some rogue logic inside the interrupt. Definitely doesn't prove that completely, but it does appear to support that assumption. That was interesting that the music came back. Like, this appears to be, like, fully playable now. Yeah, it may be this value, maybe other values. Oh, wait a minute. We did actually get a clobber here. How? Oh, this is interesting. Start of interrupt, and then we got another start of the interrupt during decompression. That makes no sense. So the reason why this fixes it is because it literally skips over everything in this interrupt. Like, because here it'll end it with this value. If it's not 0, we're going to jump all the way down here to the end of the interrupt. Just restore a couple registers and we're done. Now, so either something's supposed to write to this bit and it doesn't, which maybe that's the case, or it's a different conditional. I'm not entirely sure which that might be. Because I think here's an interesting case. Here's a value where that was, we still got a clobber, but this was 09. That can't be, because that would have had that 8 value set. And same here. But I wonder if this is overwritten here. Like it changes throughout the routine. And we're just seeing the latest value here. I wonder if that's the case. That is so strange. I think I'm going to have this break when we get a clobber. Break into the debugger. which is this. Oh yeah, and of course we're not getting those now because I set this bit here. You know, actually, what I would rather do here is I want to print out all the values that go into 2288 here. I just want to see what those are. I think I did this before, but I want to see what these are now with this new stuff in mind. We need right byte and right half word here. In fact, here I have this. And I'm fairly certain. That's what I had before. Fairly certain it's all half word rights, if I recall correctly. And we'll also do, no, actually I'll just write this. So in none of these was that 8-bit set. But this is why I don't think it, I don't know for sure that it's definitely that value. Oh, come on. Stay at the end, please. That's annoying. Okay, so right there we loaded the graphics for the title screen. And here we went in and out of the decompression routine, and we got the interrupt. And the 8-bit was not set, right? So what I'm seeing here is that that's not the only condition that can stop the clobber. So I don't think it's that. The only reason I started there is because that should very obviously keep the clobber from happening, which is just leading more to the fact that we're probably right about this. Okay. Oh, now it stays at the bottom, but I didn't expect it to. So here's something really interesting. We got OC here. Sorry, oh, what the hell? Because if this was 9 here in the lower byte, like, wait a minute. Because if this was 9 here, this will be the low byte. And that would have had that 8-bit set. And yet it's still clobbered. Okay, what? Did it just write that many values that we just lost them all? What the hell? Yeah, you might be right on this one, Daniel Collin. You check and I again. Man, I've checked and I so many times, but I am totally not against that being the problem, just seeing the bugs that we keep seeing. So in this case, what was the code again? So this is basically what's in question. In fact, actually, what I think I want to do, I want to break here. So it loads 2288 as a word, in fact. And I ate R10 into R11. Format 5. So in fact, this will... Yeah, so here's our second half word. So it's anding here. Yeah, this value is definitely 8. This is the low byte and then the high byte, which we should have gotten from here. Reading the second half word, which comes from... Should come from here, yeah. So next PC here, and then we add 2 to that. And that should definitely be correct here. Yeah, because we get the first half word, and then we increment the PC. We're going to do the same thing here. Here, rather. And read reg 1 and reg 2 as normal with these different bits of the first half word for our different registers. And we call it with reg 1, reg 2, and immediate 16. Yeah, write and read half word is word aligned. Or sorry, it's half word aligned for write and read half word. And the word, it's a 16-bit bus, so the word is actually implemented as 2 half word writes. Both of those would be aligned, but I'm definitely sure that the alignment is taken care of. But a couple things might be interesting here. I think I want to break here. But I think I only want to do that in certain cases. In fact, actually, what I want to do, let's just do this. Let's break here as soon as we end the interrupt coming to compression. Let's do that, and then we'll do. You know what? I'll do this. Break it down is... So we'll do... Whoops. That is not where I meant to put that. Cheeky as hell to do it this way, but it should work. Dark Second, I believe there's 2 masks there. One I use to mask off the last bit, and the other one I use to do... yeah, see, I do 2 masks here. One of them masks the addresses the same as the other one, and the other one will mask off that last bit. And I did it as 2 to make that a little more clear. At least that was the intention. So here we're at... Did I get the wrong address? I did, yeah, because it broke right after it stepped there. Although, that may be helpful, actually. Because if we break... Yeah, because this is comparing the reg PC. I'm gonna do this after we step to make sure that we get the right address. That'll make it easier for me. Which then there's no reason to do this in sort of 2 steps here, but that's fine. Don't really care too much. I'm getting sick of this bug. I'm gonna be so mad at myself if it's this simple. So in this case, what I like about this situation here, let me bump up my font size for you guys. Whoops, not mean to do a new terminal. What I like about this situation here is everything is in the registers at this point. We have, if we look at the code, and I'm assuming this code is correct because it looks correct. It looks very correct to me. We have some value in R10, which is a word value, and it should match exactly the value here. So if we go here, and then we do mem, we should see, so this is 02070000, and if we do the registers, R10 should be 02070000, which matches exactly, right? So this is R10, and we're going to AND that with 8 and store that in R11. In this case, flags are a little hard to read here. I may change those to print that a little differently, but let's do one step and then print out the registers again. And now R11 in this case should be 0, right? Because we're going to take this 16-bit value here. And in fact, I think we actually, in AND I'm pretty sure we 0 extend that to 32 bits. And then do the AND bitwise AND here. Then we set the 0 and sign flags based on that result, and we can check that yet again. Which should set the 0 based on if the value is 0 completely, and then the sign if this high bit's set. Now in this case, the sign is never going to be set. In fact, if I pull up the data sheet, it should actually say that the sign is always going to be 0, because if we're going to sign extend the 16-bit value, then this will never happen, because the sign extend version of the 16-bit value will always be 0, so it doesn't matter what's in the register. So that should be the case. Just gonna pull up this. Can't remember which manual to get the data sheet, although I don't think it was the data sheet that we needed, but I think it was the architecture manual that we needed. And if we look for AND I, which was not found, which is weird. Go down to where the instructions are, and we should find AND I somewhere here. Here's AND I. Immediate 16, reg 1, and reg 2, which is exactly what we have. And we take general purpose reg 1, And we AND that with the 0 extended immediate 16, which is exactly what we have, and then we store that into reg2. Here we see sign is 0, because that's always going to be the case. 0 is 1 if the result of this is 0. Otherwise, it's 0, right? And we do this as a Boolean. So instead of 1 and 0, we do true and false here. And yeah, sign is 0 and then overflow is 0. Now for the overflow, I think I just explicitly always set overflow to 0 in that case. So as you can see here, I always set the overflow to 0, and then this should give us the same result that would have given us. Yeah, because we do it based on the result. And then here I set reg GPR to the result here. The only time where this wouldn't hold is if the target register was R0, because then in that case, setting R0 to this will do nothing, but then we still set the flags based on this result. And I'm pretty sure that I suspected that at one point before, and I think I changed that and it broke stuff. So I think that ends up not making a difference. I think it actually sets it based on the result, even though it says that it sets it if the grreg2 is 0. So I don't think it's anything weird like that. And plus that wouldn't apply here anyway, because in particular, our we never touch R0 here. But here's what I really don't like about this, is that it looked like in the output we had a case where this did not give the right result in the flags. So BZ is going to test our 0 flag. In fact, I can double check that now as well. If I remember where this is. I'm pretty sure all the branches have their own instruction here. Which is here. So BZ should be the same as, here I have not Z, here I have Z, if the 0 is set. Oh, that was set F, not the branch, but I'm pretty sure the branch is like the same logic. Here we go. Yeah, so here's our conditional. We get these conditional bits, and then we take the branch BZ here. So a couple things that I would suspect if this logic is not happening correctly. First of all, either and I is not doing its job. Or perhaps this branch isn't doing its job. JR, I would expect to work. That's a jump relative, and it always jumps. I can't remember if JR was covered here or not. I don't think it is, actually. I think JR is its own thing. And it's, yeah, we literally get the target, and then we just jump there. Take that many cycles. So what would be a good way to test this? I think one of the things we can do or here's something we can do actually. So we know in this case the AND worked, right? Because we had, in the registers, we had our 10 was 0702, and then our 11 should be 0 in this case, and it is. And so then we're at 1C here, which is this guy, branch of 0 to this value, or to this area. And if we branch, we should take that. So if I step, we're going to be at 2.2. Okay, so we're good there. Let's just run through this a few times. So in this case, we have, if I look at the registers, we had, again, this is going to be the same case. So if I step and look at the registers, our 11 is going to be 0. And if I step, we're at 2.2 here. So the next thing I want to try is, yeah, just do this a couple more times. In this case, Same thing. So I'll step twice. Yep. And then look at the register again. Step twice. And where we should be. And now we're down here. No clobbering has happened. Oh, believe me, I've looked at other emulator code for this. Here, let me turn off the audio there. For that. And so here I want to do the same thing. So in this case, we're going to end it with 8. In this case, this was OC01. Should make sense because those are the ones where we've seen 01OC. In fact, I think in these dumps here, we're going to see 01OC here. And in this case, the 8-bit is also not set. Because, yeah, it'd be this bit here. So if I step twice, we're going to look pretty good. In fact, if I check the registers here, R11 is going to be 0. So that's what we expect. And of course, we clobbered there. I'm going to go back here. OC02. And we're where we should be. I'm going to let this go to the main game here. And here, 0401, so this will be the same case. Now, I don't know if I mixed up the bytes or something and just thought that I saw that clobber when it shouldn't have. Because here we're definitely not seeing that 0401. This should be correct. Okay, here, this bit should be set. Right? 04OA. And just, yeah, that worked correctly. So if I step here, now R11. Am I reading that right? Did that not work? Just to be sure I'm interpreting this correctly. At this point, we were at this address, 2A. Wait a minute. Wait 1 second here. Did I test this correctly? Now I'm seeing addresses here that I did not expect to see. I don't think this is a different interrupt handler. I think this is different code. In fact, 4.2a? What am I doing down there? Oh, that's here. Did I just step too far or something? What did I do here? Okay, we had 1.8. And then I stepped, and then I stepped. And then we were at 2.2. And then what happened here? Did I continue there or something? And then I ended up at 2.6, and then I print out the registers. Oh, do we have a different watch that broke there or something? I think I messed something up there. I'm just going to sit here and do this again. 0402, we should be fine. Continue there. Oh, okay. C01, so we shouldn't have any problem here. CO2, so we shouldn't have any skipping over stuff there. Now I'm going to let it go to the game again. I actually think I know what's happening here, by the way. What this bit is supposed to be doing. Wait a minute. That's what I think I'm seeing is double start of the interrupt. Because here's what I think is happening. The interrupt starts. It checks the value of this value here. And then it checks that 8-bit. If it's 0, or sorry, if that 8-bit is set, then we're going to basically skip everything. Otherwise, we're going to enter this routine, and the first thing it does is it sets that 8-bit and then stores it back into that value. Stores it back into that variable. So I think that 8-bit there is meant to keep this, like if the interrupt does fire twice, it keeps it from doing anything. So this is really interesting, actually. Because here, why did this print start of interrupt during decompression and then a clobber and then start of this? So what did we have in here to do this logic? Because we had... Okay, yeah, so if it gets to this position, then we're going to print that. And the clobber happens if we hit any of the watch points here while we're in the interrupt and decompressing. Now, this is somewhat interesting because this would basically say that a clobber happened, but we didn't get to this address yet, which is really weird because this address is like right at the beginning here. And why would we have gotten a clobber then? Or is that actually, you know what? You know what that might be? Wait a minute. Why is that happening? First of all, why would it start this interrupt twice? I don't think it's... I'm really confused here. Because, so here, if the PC is this value, so entering the interrupt, 292. Oh, wait a minute. This isn't the start of our interrupt code. Start of our interrupt code is here. It should disable the interrupts here. There is a duplex exception, but I don't expect that's what's happening here. Because this should keep it from doing that. This should keep it from doing that. Oh, wait a minute. I'm gonna print this here. Yeah, this actually does allow interrupts within other interrupts, but you're masked based on a couple things. let me just see something here. This right here is so interesting. It definitely entered this exception twice. Let me print this as well to see if we actually do get this happening twice, because that is so wrong, I think. Now, it's weird that that only happens some of the time, but it may point us to something. That can't be it. I'm gonna be so mad if that's it. Okay. Oh, I still think that probably fixed something, but that can't be it. I'll explain what that was in a sec. Okay, so here it actually did return from the exception before I entered it again. Wait a minute. Right. So my clobber detection is actually not quite correct. Because it's possible that we enter and leave the exception without ever hitting this routine. Although, to be fair, I'd find it pretty strange if we hit this and then didn't hit this. But we're definitely not entering that twice. We got the exception and then some condition didn't happen and then we left the exception. But I don't think this clobber here is correct. In fact, I will change these addresses here to be the actual start and end of the handler here, rather than the start and end of the function that's called in that handler. And we'll see what we get. Oh, yeah, right there. Yeah, okay. So there it was. Yeah, because we actually did the interrupt handler going in. But going out, we only had return from that one function, which is not correct. This one should be our little epilogue here. So if we do that at least, then we shouldn't get the false clobber. Although, this change right here might actually be correct. This is what's going to early out. I need to check the data sheet to see if we can do this in the meantime, because I actually think that was correct. Oh, come on. Why can't this find the exception thing? Just have to look this way. Exception processing. Okay, one of these. If an exception occurred, does this MPU set already been set? Proceeds 8 for exception, duplicate exception. Saves this, writes the exception code to EICC. The interrupt is not accepted if the interrupt level n is lower than the interrupt level. Okay, that was actually, I think that's actually correct. That this is like lower rather than less than or equal to. Okay, so we'll ignore that. But I think yeah, just my detection here was wrong, and that's why the clobber thing showed up there. So I don't think the interrupt is firing twice. I think it's just that we didn't detect that it left properly. For example, if I do this, we should still detect clobbers. Of course, I'm outputting too much stuff, so we can't really tell there, but... Yeah, so here we're getting some clobbers here. So the detection should still be correct. In that case. I'm going to let it transition here. We'll see if that... Yeah, so here we got the proper... Here it didn't say clobber, but we entered the interrupt, and then we entered it, and then left it, and then entered it again. And then here we go. Right, so that... It wasn't that it was double firing, we just detected that wrong. Which is good, because that would have been weird. Yeah, so in this case, things should still be the same. But it was one of these cases where I seem to have seen some broken logic. And I just want to make sure that I'm actually seeing that correctly and not just screwing something up here. Okay. I'm getting so frustrated with this. So this was kind of the most interesting thing. So we know that at least this is a mechanism to stop a double interrupt in case that happens, which shouldn't happen. It shouldn't happen anyway, but that seems to be what that mechanism is for. Maybe it's possible that that's set elsewhere. Although I'm going to doubt that. I just noticed something really interesting. I don't know if you guys remember. I turned off my system audio. I don't know if you guys remember when I was listening to the sound output on the device, and the oh, I'm starting to get really tired now. The sound. So when I transition from, so here's first of all something interesting. If I move around the arrow keys, a sound plays, and then our sound works again. Interestingly enough. Another thing, if when I transition away from this, listen to the sound. Doop. That sounds really correct, by the way. Whereas if I don't do this, we get like doo-doo-doo, like a 3-tone sound. And I remember from the hardware that it was 2 tones like that, where now we're seeing 3 tones whenever we get the corruption. So might be something related still. See how there's like 3? Whereas this just had like 2 tones, and the 2 tones is what I remember hearing from the hardware. So how might this happen? Like let's assume for a second that this was the only place that this variable was set. Right? Then this interrupt would have had to have fired before the decompression routine started. Maybe. But now listen to this. The 2 tones. So that's correct now. And let's see if I don't do anything else in that menu and see if that still works out. Man, that sounds really correct. Let's just see if there's any other places that write this. Let's just do a proper watch point this time. I'm also going to get rid of the debug printing that we did here because I don't think that that's actually relevant now that we've seen that. Data Colin, if this would have been happening on other platforms, I would have started a hunt for multi-threading issues. Absolutely. And that's basically what this is if there's another place that was supposed to set this first. Which is interesting. Yeah, okay, so I was going to enable watch for this particular address. Whoops. Are you kidding me? This seems to be touched a lot. R person, thanks for the follow. Yeah, I did revert the interrupt level change. This is should be less than here. So we're good. Let's disable the audio again. A 418. So this is during our interrupt routine, where we expect this. We expect to see this. But it looks like we are seeing this a couple other places. Oh no, 4.2a is also where we would have expected to see that because that's here. After it's ORed here. So 2a and 1.8 are where we kind of expect to see that. And 4.3.4, which we also see here. What? Oh, it ands it with this other value. So it just stores that as an immediate value and then ands it and then stores it again. Man, this compiler sucks. 508. Yeah, it reads it here again. Checks the 2-bit. But here it's only reading from it. Here it writes again, though. But again, it does the same math that we saw before. And then it looks like we have some stuff down here, which I believe is at the end of this. So I'm a little bit concerned about this, actually, this -9 here. So this should be move immediate. Yeah, because we have a sign extended immediate 5. Get the value there. So if we look at what's our immediate 5 in this case? Format 2. Here. Immediate 5 is the first, yeah, just the lower 5 bits of the first half word. Which in this case is -9. I think that's correct because of 2's complement. In fact, if I do pull up the calculator here. If we do, for example, programmer, and we take hex, should be the same as 1, 0 if we AND with 1F. Or wait a minute. 4, 0? This should be 0. Shouldn't it? Right? Because if we and 4, 0 with 1F, we should get 0. Am I just full of shit or something? What does my disassembler say about this? Where did I put that? Was that emulator? Here we have the move. So take the immediate 5. Which again should just be that first half word in those lower bits. So we've already masked everything off, so it should be 0 in that case. And then I take that as an I32, shift it left 27, and then shift it right 27. And that should be correct because 27 plus 5 is 32. That should be the right number of bits. In fact, if we took 1F and we shift it left by 27, then we're going to get F8, which I think is correct. Yeah, because that'll be the top 4, and then, yep, that should be correct. And then right shift that 27. And we're going to get our 1F again here. Oh, no, wait a minute. No, because that will do a sign extend, right? So if we shift left. Yeah, okay. No, that's actually correct if this is supposed to sign extend. Although it's not if it's 0. And then how the hell... Wait a minute. Why the hell would that be? Hold on. This is frustrating me now. So if the immediate 5 was... Okay. We're looking at 3740 like this. This is in... maybe this is Little Endian. Can't you say I'm getting tired? If this were Little Endian, then we would actually have 1F here. And go back to my calculator here. 1F left shift 27 is going to give us this here. Actually, here's what I'm going to do. I'm going to look at -9. Right, and if I take this left shift 27. Whoops. Left shift 27. Let me get B8. That seem wrong to anyone else? Am I just like too tired to do this? Or let me look at this. Let's do we're gonna go to this address. We're gonna hit mem, right? 3740, right? So this is the lower part, 37. If we take 37 in hex and we AND that with 1F, we're gonna get 17. That makes sense. Now, if we left shift that by 27 in decimal, then we get B8. Okay. And then if we would have, if this were sign extend, then this would have been correct. So then if we get rid of this and we do -9, we should get the, and then we also left shift that by 27, we're going to get the same B8. Okay. So that -9 is correct. That -9 is correct, I think. And then, that's going to be sign extended. And so then it's going to AND it with this. And I think we're going to be okay there before it stores it. Okay. Now I feel okay about that. And next time we see this is 522, which is again within this range here. And we're loading it there and ANDing it with that. Okay. We're basically only seeing, we're only ever seeing it touch this value within this range, it looks like. Within this piece of code. Which is a little concerning. Let's do this. Instead of doing a proper watch there, let's watch this value. Or how do I want to do this? I want to see if this value is touched from anywhere else other than within that range of code. Maybe that makes sense. So if I wanted to do that, let's do this. If it's decompressing, or that's actually not what I want. I want self is in interrupt. No, that's not what I want either. I want to know if the PC is within that range and we got our watch. Then we're going to cancel the watch. Right? So if this one, so we'll enable the watch, but then we're going to basically disable it if it's here. I could also do this within the CPU, but I'm just going to do it here. And we'll do, this is the exit here. Want this to be inclusive. Yeah, so I'm still going to set up the watch, but we're going to ignore it here. In fact, I can print that. Yeah, so now we're getting a bunch of these that are ignored. right? And so that's the value being touched, but it's being touched within that routine. There, just touched it outside of that. 8.9a. 8b 8.9a. That's not up here, is it? Okay, here it swaps that 4-bit, interestingly enough. Yeah, that's there. Here it writes a value with the 8-bit set. 5a6? 8b586? That's not a place where you've seen, is it? That's here. No, that's 80586. Okay, so there. So here it totally wrote to that right before this instruction. Let's do F8 B5 A2. And that was not the right place. We'll go FF8 B4, or sorry, B5 A2. And there it's stored this here. Let's go one above that. B5 9E. So this is going to write a value that included that bit. Let's F8 B5 9A. Okay, so at this point, it already had to have been that value. That bit had to have been set before this. D doesn't include that, does it? I don't think D includes the 8-bit. Or does it have to, actually? It does, actually, yeah. So, okay, wait a minute. So the write actually happened within that routine. And then this was checking it and writing it back. So I don't think that's significant. Unfortunately. They wrote 702. 700 there. We're getting a bunch of clobbers here, aren't we? Does this seem excessive? Hey, I think this is triggering sounds. At this point. And now the difference between 1 and 9 again is that 8-bit, interestingly enough. But it's ignoring a lot of these watches here. Let's do the symbol here. Oh, wait a minute. Here it actually definitely sets that 8-bit here. Ep.033. This is definitely setting that bit, actually. So I only checked if the PC is within that one function that we were looking at that happens, that's called if there's a frame interrupt. I mean, the things that could be triggering the sound could be coming from another routine from that interrupt. It could be coming from many different places. I don't think it's coming from another interrupt. I disabled the timer interrupt, I remember, at one point, and that didn't help, if I recall correctly. Just to be sure, I'm actually going to try something here. Or actually, we want to set that bit, don't we? Just want to try this. Or that was actually not what I wanted to do. I wanted to do that when reading it. Yeah. That was read half words. We're going to do that in that case. I'll do this actually. The interrupt, it's a start of frame processing interrupt. Or it's actually the video hardware interrupt. But the start of frame processing is the one in particular that at least checks. I'm sorry, I'm getting too tired to start explaining things well again. I'm just gonna try some stuff here. Here. Let's see if we always return with that bit set. Be curious to see. Maybe we need to let mute here. But yeah, it's a video hardware interrupt. And if it's the start of, so the video hardware interrupt can fire under a number of conditions, and then we can get the cause in a certain register. If that cause is start of frame processing, then the code that we've seen that will check that bit and then jump over stuff, that will get run if it's start of frame processing. Otherwise, some other code might get run. So it might actually be quite relevant, actually, if another piece of the code was touching this bit, another piece within the same interrupt, or within, yeah, within that interrupt handler, but not the part that we're looking at. So here's another thing that's interesting. If I always return that bit being set, the sound never plays, and we never get clobbers. So empirically, like what we expected earlier, it appears that the sound, the part we've been looking at, is probably related to sound. And this bit appears to control whether or not the sound is enabled or disabled. Or whether or not the sound is playing or not playing, I suppose. And so if we can find other places where that's enabled and disabled, and maybe we're on to something. Again, though, nothing we wouldn't have expected by doing this, except that the sound completely stopped. But that's kind of what I suspected. Interestingly enough, it's also not changing screens. It's not going into the demo mode, which could actually make sense because I think it goes into the demo mode when the song stops. Now that I think about it. That's probably why it's never going there. Okay, so I think this bit of this location is definitely whether or not the sound engine should be running. And I think that main piece of code we've been looking at is definitely the sound engine. If that's a way to put it. As is evidenced by 1, the sound not playing, and 2, the fact that it's not transitioning into demo mode now. When I basically disable writing anything other than, or if I make all reads from that, have that bit set. This could also make sense why I saw why I got a bunch of breaks in that intro, because that's a little looping piece of music, I think. And it's possible that when that loops, like the song ends and then it plays it again. You know what I mean? You cannot read from the VSU. It's or at least none of that's implemented. In fact, I think I panic whenever it tries to. So the game's definitely not trying to read from the VSU. And I also disabled the VSU a couple weeks ago, and that didn't help. So I don't think it's the VSU. I think it's some logic that's making this sound engine play when it's not supposed to. But I have been at this for 3 hours today. So I think I'm going to call it quits for now. But basically what we learned for sure is that this bit can at least help us not clobber stuff. And I think definitely the place to start next week, or next time I look at this, which will probably be next week. I think the next place to look for this again is, where is it writing to that value? Colin, we learned a bit. Exactly. You could say we learned a bit. Yeah. Yeah, a little bit of progress. I think some things that I can share that I'm suspecting. I think either something in the CPU is broken, and then we're getting some branch or something that's skipping over some code that's supposed to disable this, or we're not masking out that bit properly. So like the logic is trying to disable the sound and just isn't because the CPU is broken. And the reason why I'm still suspecting the CPU is that due to the bugs in some of the other games I've seen, especially the one where the lasers disappear in Space Invaders, assuming they might be related, that's what I would suspect. The next thing I would suspect is that our logic for when this interrupt fires is still wrong, and that somehow, like if the timing were changed so that it would like when the different conditions for the video interrupt happen, like maybe it is what if it did something like enabling the interrupts and then disabling the sound, and we got the interrupt too early? That could also make this happen, especially if the sound bit never got disabled and then an interrupt fired, and then that overwrote whatever that value was supposed to be as it transitions to the next screen, because that would explain why when it starts clobbering, it doesn't stop. Unless that's just the interrupt firing multiple times within the same thing. But it appears that it's safe for this interrupt to fire while the decompression is happening. I think that's still correct, especially knowing the logic of when it fires and how and the registers that this is setting on the video hardware. I think that's still correct, but I think it's something else that's not clearing this bit when it should. Either if that's an interrupt firing too early or something else. Debugging, you should try hacking a different emulator that doesn't have this bug to watch for when this bit changes. One of the things that I did when working on my Super Nintendo audio unit emulator, it's a mouthful every time I say that. One of the things I did that was actually really useful there is I went in and I took my code for just the CPU. So this was like really early on in the emulator, and I had only had a lot of the CPU done and then some of the peripherals. And I was having a lot of really weird bugs, and I didn't know if it was going to be the peripherals or the CPU. I didn't really know where to look. So one of the things I did is I took someone else's emulator and I refactored the code so that our CPUs had the same interface. Now it actually changed. I had to hack around a little bit of the peripherals there, but it worked enough. And so at that point I could swap out the CPUs and just log all the registers with the same format from both of them as it would run. And when I had that, then I could just dump all that stuff to text files and see where stuff changed. After that, it was actually really easy to find what the bug was. It was actually, I didn't have some parentheses around some shifts and stuff in that case. And I was kind of hoping to avoid doing that for this one, but it would be really nice to be able to rule out the CPU being the problem in this case. So if it takes me, I might get frustrated enough to the point that I just say, screw it. We're putting a C API on this CPU, and then we're going to take mednafen or something and just sort of hack the code until it matches. Maybe we'll do that. It may not be very easy to do that, and kind of one of the reasons why I've held off on doing that is that I don't think it'll be very easy to do that because when I did the Super Nintendo one, both of those were C++. But in this case, it's Rust versus C++. And at least when I refactored that other code, it was not a simple task to make the interfaces match, like the way that the CPU, when the CPU would drive and when the other code would drive, did not line up. And that's really unfortunate because it sounds like that was a simple task and it wasn't. So I'm only going to do that if I decide that was, after all, easier. And at this point, it probably would be. But yeah, I really wish it were that easy. But that's another thing that we can try if we can't find this. But I'd like to I think reverse engineer a little bit more of this code first, and just see what's going on here. So I think, yeah. Anyway, made a little bit of progress today, and I'm pretty happy about that. So thanks for hanging out, guys, and I'll see you next time.